is 1, 0. And there should be h bar over 2 here, I think. Okay. So based on this, we can deduce that, well, the S plus looks like h bar over 2. 0, 0, 1, looks something like this. Okay. And then you can also get the S minus is equal to h bar over 2. 0, 1, 2, 3, something like this. Okay. Because the action of the S minus, the lowering operator, is just going to take the spin up state, turn it into the spin down state, and everything else is 0. Okay. So from these two, we can construct the Sx and Sy. Okay. So we get that the x direction spin, this is given by 0, 0, 1, 1. Right? Because why? It's just a sum of these two. Right? Oh, if we develop it, okay, so sorry. There must not be 2 here. Okay, this goes to here, no problem. And then you can also get the Sy, and this is h bar over 2. Okay. 0 minus 9. 0. So now everything is reduced to 2-component matrices. And everything about spin is incorporated in these matrices. Okay. And now if we forget about h bar over 2, the dimension, the unit, then these 1 minus 1, this one, and this one, these are called the Pauli matrices. Okay. Pauli matrices. And we denote them with sigma. Okay. Sigma I being x, y, or z. And the Pauli matrices you can use the Pauli matrices to do any kind of 2-level system problem. Because any 2-level system, it becomes a 2x2 matrix, right? And the 2x2 matrix can be decomposed onto the Pauli matrices. You can prove this, and maybe I should let you prove this in the homework. So I'm saying that for any 2x2 matrix, okay, so maybe this is A, B, C, D. Okay. It's possible to decompose this onto the Pauli matrices by writing a vector. Let's call this some vector M, okay, dotted with the vector this, and this vector is given by x hat sigma x plus y hat sigma y plus z hat sigma. Okay. And then once you have considered one problem involving the Pauli matrices, say you solve the problem of an electron in a magnetic field, then any 2-level system is exactly the same as that one. And you by changing the magnetic field, the direction of the magnetic field or the intensity, you can use it to model any kind of 2-level system. That's the power of Pauli matrices. Everything comes down to the algebra of Pauli matrices. And in your homework, you're going to prove this.
Right. You need the identity term in the right.
Yeah, right. But okay, so actually you need a plus, maybe plus something and not times the identity operator. But I remember if we, I'm not sure if I'm correct here, if we require this to be unitary, then there's no identity.
But if you just don't put in identity, the trace is always 0.
Yeah.
So the line before you should have M0 times I or something.
Yeah, something.
The identity is part of the Pauli matrices needed for completeness.
Right.
The x, y, and z components are not complete.
Okay, so an easy way to visualize this is how many matrices do you need? How many basis matrices do you need to represent an arbitrary 2x2 matrix? You need 4, right? Because you have 1 here, one here, okay, one here, and one here. And then the poly matrices and the identity matrices just different linear combinations of these matrices. Okay, so you need 4 to be complete. This is why you need to augment this with the identity.
I have a question.
Yeah.
So if we need 4 bases, which means this space at least dimension of 4.
You're right. But this space has 4 degrees of freedom. All right, so now let's talk about something more about the splitter. Okay, so we've written down these eigenbases of the Z-spin, right? And now let's think about the valid, the correct superposition of these states. So it's certainly true that I can write for an arbitrary spin state, maybe alpha and beta here, okay? And alpha being the amplitude in the up spin direction and the beta the amplitude in the down spin direction. And the only requirement I have on this is alpha squared plus beta squared is 1, correct? Okay. So I can think about this as some kind of a vector with a unit magnitude, right? With a unit norm. And this kind of vector can be parameterized by 2 angles because since the norm is defined, okay, the only freedom I have is the direction, and the direction is modeled by 2 angles. Okay. So let me write this out as alpha is equal to cosine theta over 2, and beta is equal to sine theta over 2 e to the minus I t. Okay. Let me define it this way. So why do we define it this way? And why do we use these half-angle formulas here? So you'll see in a minute, because that gives us a very intuitive pictorial representation. Okay. So now, remember we constructed some operator before. Let's construct a vector operator S. Okay. That is the direction of the spin. So this is x hat times s plus y hat s y plus z hat s z. Yeah, this is a vector operator. Okay. And once again, we have the confusion. Okay, these are the direction, the unit directions, not the operators. So now let's compute. In this state, what is the expectation value of this operator? So that's given by this. Okay. And we can do a component by component. In the x component, we have, okay, so we have alpha, beta, 0, 1, 1, 0, alpha, beta. And then of course you get the h bar over 2, but let me factor out the h bar over 2. Something like this. Okay. What does this go into? This just rotates this by 90 degrees, right? So you get beta alpha. So, and then in the y component, you'll have alpha, beta, 0 minus I, 0, alpha, beta, right? And then in the z component, you'll have alpha, beta, 1 minus 1, 0, 2. Okay, so pretty simple. So this one goes to alpha beta plus beta alpha. Oh, sorry, these should be complex conjugated. That's why it makes a difference. Correct? These should all be complex conjugated. Okay. Y hat this one, there's a minus I here. Okay. So let me take out the factor of I. I times, right? So minus I goes with B, the beta, right? And then this beta goes with alpha conjugate. This has a minus now. So this is minus alpha conjugate beta. Okay. And then beta I alpha. So beta conjugate alpha. Right. And then is plus Z, what do we get? This here is alpha magnitude squared, right? And then is minus beta magnitude squared, right? Okay, so now you'll see why we define the half angle, because now we can combine them into full angles. So the alpha, by convention, is a real number, right? So we get, in the x direction, let's carry out the algebra. We will have so cosine theta over 2 sine theta over 2. Okay, and then is plus. Okay, so this is e to the I phi plus e to the minus I phi. Right? Now how do we combine these? Cosine sine must go to a sine because it's on. Right? So this is just 2 times sine. Or no, I mean sine of 2, right? So this is sine theta over 2. And let's give this 2 factor to here. Okay. And what does that mean? That gives you a cosine phi, right? So the x component is what? The x component is sine theta cosine phi, right? So now you can guess what the y component is. The y component is actually y, okay, sine theta sine phi, because we have this minus here. Okay, and then the z component is z cosine theta. I'm not going to carry out all the algebra here. Okay. So now it has a very nice pictorial representation. So I can write a spinor state like this onto a sphere. And the sphere has unit norm, unit radius. But the direction is defined by the theta and phi. Okay? So let's draw a sphere. Okay, this is a sphere, right? And the theta direction, okay? And the projection defining the phi direction, the phi. Okay. And then what is this? Well, this is just the expectation value of the spin operator. And it's a vector operator, so the expectation value is a vector.
The vector doesn't end there. When you draw that vector up, it doesn't end on that parameter of the circle. It should end on the surface of the sphere.
Yeah, right. So that's what I'm trying to say.
It ends on the circle. That's not the right circle it should end on.
Okay.
It should end on the surface of a sphere.
Right, right. So let's draw the 3D thing. Okay. So imagine this ending on the sphere. Okay. This point is on the sphere. If you look over it, you still see some part of the sphere. So, anyways, so now we get that based on the theta and phi, we can narrow down one point on this sphere, right? And this is called the block sphere. And in recent times, the block sphere received some more attention because of the advent of quantum computing. Now, without going into quantum computing, let's just say one thing. Okay. What is the information that you can carry with a classical bit? 1, 0. And if I have a classical bit, okay, 1, 0, I carry 1 bit of information, either 1 or 0. But with something called a quantum bit, which is, in every way, it's just a spinner. Okay? With a spinner, how much information you can carry? Okay? Based on the possible values of alpha and beta, you can carry information on the whole sphere. The possible informations are here. So just one quantum bit gives you, how many points are on this? Infinite. Right? Gives you a lot of information, and of course you need to resolve those points. So it's not that good, but it's pretty good. Okay. So this is the blocks, the concept of the block sphere. And then towards the end of the course, we're going to use this block sphere to talk about quantum computing. All right. So now, before we move on, let me tell you about a classic experiment. And this experiment motivates the magnetic moment of the electron and so forth. That is the Stern-Gerlach experiment. Okay. This is before quantum mechanics. How much time is it? Oh, too bad.
Maybe you can spend 2 minutes to talk about
All right.
Gerlach experiment.
Okay, 2 minutes on the Stern-Gerlach experiment. All right. So the Stern-Gerlach experiment is set up this way. I have some oven, okay, and the oven is going to spit out some silver atoms. Now the silver atom, the outermost shell is the 5s, and there's only 1 electron in the outermost shell. So silver has valence 1. Okay. So now we have some oven, okay, and it spits out a beam of silver atoms. And these atoms, although they're extremely heavy, their spin degree of freedom looks like just 1 electron, because all the lower shells are complete, and you have an even number of electrons with no spin. And then you put some screen here to filter out just these 1 beam of silver atoms. Okay? And since this is a really hot oven, we have no idea of knowing what the spin is. So in here, you can say that this vector comes out random. Okay? So the electron is scattered all over the block sphere, the silver atom. All right. So now I'm going to subject this to an inhomogeneous magnetic field produced like this. So there's an inhomogeneous magnetic field in the z direction, and the strength of the field is increasing in the downward z direction. And they make this by having a wedge in one of the magnets. Okay. Whenever you have a wedge, you have a stronger field. So the field might look something like this. Over here is very strong, and in here, because it's smooth, it's not as strong. Okay. So when you have a inhomogeneous magnetic field here, now the magnetic interaction, but I don't have time to go into this. The interaction energy is given by the magnetic moment dot with the B field. Okay. So remember, it should be a minus sign here. Yeah. So now remember what is the force? The force is the derivative of the potential energy. Right? This is some kind of potential energy. Right? So we get that the force is in the downward, in the minus z direction, and then is mu times dB dz. Since b is increasing in the downward direction, this is a negative thing, right? And then we get a force that's minus. So in the end, what happens is the spin down electrons is going to experience a force that's downward. Okay. Spin down. And then the spin up electrons are going to experience a force that's upward. Okay, something like this. But now, before quantum mechanics, people didn't know that the spin was quantized, right? So they expected a whole range of different, they expected this beam to be split into a fan. Okay. But what they found was, they only found 2 lumps. Okay. And after you do the math, it turns out that, okay, it must be that over here, the electron must have a magnetic moment. That's some multiple of h bar over 2, and this is minus h bar over 2. So this is the first thing they found. Well, something is quantized. and they deduce the value of h bar here. Okay, that's very close to the h bar deduced by Planck and Einstein, respectively. Okay, so something was going on here. Now, what's even more interesting is now that, okay, let's say this is the SZ plus beam, this is the SZ minus beam. Okay, now if I have some shutter and I filter out in total the SZ minus beam, and I subject this beam to a new Stern-Gerlach experiment. Okay, so this goes into here, but now this is in the x direction. Okay, so the inhomogeneity in the field is in the x direction. And again, I will see two beams. Okay. Well, being the x plus beam and the x minus beam. Okay. So although we have figured out that the spin is in the plus z direction, it's actually also equally likely to be the sx plus and the sx minus direction. So this is not the all of the peculiarity. So now if I once again block this minus component, okay, and I subject this beam again to a Stern-Gerlach experiment in the z direction, what I will get is once again two beams come out. Okay. So classically, if you think about it, over here you have eliminated all of the things that comes out of the orbit with the minus spin here. You have eliminated them. But then, if you do this experiment, okay, because of this intermediate experiment, you have put in some minus z spin component again. Right? So this was one thing that puzzled people for quite a long time. This is the Stern-Gerlach experiment. Okay. All right. So I guess that'll be it for today.